So hello everybody, my name is Yisroel Mirsky. I'm a PhD student at Guri University. I'm also a project manager at the BGU Cybersecurity Labs. And what I'd like to talk to you today about is bridging air-gapped networks. Most of the works I'm going to show to you today were authored by Mordechai Guri, a colleague of mine, a PhD student in our labs, mentored by Professor Yuval Elovici. But since Mordechai Guri was not able to come today, I, as a co-author, will be presenting in his place. So let's begin. What is an air-gapped network? So the typical approach to a security network looks something like this. You have the internet or some public domain, and you have a private network. And the private network is separated with some sort of firewall or network intrusion detection system. And as we know, the attacker wants to try and get into that network from remote, and he also wants to perhaps have some malware exfiltrate information out of the network back to the attacker. And we know that there are holes in this approach, so they came up with an idea called the air-gap approach. The air-gap approach is the idea that we'll put a physical disconnect between our private isolated network and all other public networks. The idea is if there's no connection between our private network and our public network, then the attacker can't send information into the network to his malware, and he can't exfiltrate information from his malware out. So that looks something like this. You have an air-gapped network, some sort of installation, and you have the public network such as the internet, and the attacker, since he has no physical connection, no Wi-Fi, no Ethernet connection, he can't communicate with the network and he can't attack that network. Some examples of air-gapped networks that exist today are military defense systems, financial systems such as a stock exchange, industrial control systems, critical infrastructure, power plants, refineries, air traffic control, command control centers, computerized medical equipment, and so on. But we know that putting an air gap is not a perfect solution. Here's just a small list of malwares in the last few years have been found to infect these air-gapped computers in one way or another. For example, the Stuxnet virus, which infected the Iranian nuclear power plants, even though the Iranian nuclear power plants were not connected to the public network. So some sort of infected USB was plugged in at some point, perhaps, and infected the network that way. So how does that happen? What are those steps? So the first step essentially is the initial infection. In the initial infection, malicious or deceived insider plugs in a USB or some other media into the system, infects the network with the malware. Or another option is that there's some sort of a supply chain attack happens where the hardware, perhaps the USB keyboard or some other peripheral is infected at the factory when it is made, and then brought into the isolated network and plugged in and then infects the network. After the isolated network has been infected with the malware, the second step is for the attacker to have the malware perform some sort of activity, whether it be stealing sensitive data, manipulating control systems, deleting records, and so on and so forth. So the real question is, and we know that malwares can get into air-gapped networks, but how can the attacker communicate with his malware once it's in the network? And how can he get information out of the networks because of the air gap? Now, there are a few different kinds of channels we'll talk about today. One kind is inbound channels. Inbound channels are where the attacker wants to send information to his malware, and outbound channels where the attacker wants to pull information out of the network. Some examples why an attacker would want to use an inbound or outbound channel. So for an inbound channel, he may want to send the malware some command to attack at that moment, giving him the flexibility of when to attack. He may want to lay dormant for a while, right, and then attack at the most opportune moment. He may want to send updates to the malware, new modules, fixes, perhaps change the encryption key. And for outbound channels, he may want to exfiltrate information, passwords, documents, key logs, and he may want to get reports on his attack, which is very advantageous for him to know whether his commands have been received by the malware at all, and what is the progress of the lateral movement through the network. So the bulk of what we're going to talk about today are the different methods of exfiltrating information or bridging the air gap, sending information, building these covert channels from the air gap network to the public network. And there are three general channels for if you're doing this. You have thermal channels, you have acoustic channels, sound, optical channels, and radio channels. Of these 11, which we're going to talk about today, 10 of them were discovered in our labs. So let's start with thermal channels. The first type of thermal channel we'll talk about is called HVACR. Now, the idea is that modern computers have thermal sensors in them, and quite a few. You have thermal sensors in the CPU, you have thermal sensors on the motherboard, and it's mainly there to be able to regulate the temperature of the computer to protect the computer from not overheating. Now, the idea is that if we can change the temperature in the room, raise the temperature in the room, and lower the temperature in the room, the computer can pick up these changes and interpret that as binary information. So the question is, how can an attacker manipulate the temperature in the room? Right? Well, in many cases, insecure networks are overlapping in the same physical space as the public as private and protected networks. And one of those types of networks, as an example, is the HVAC system, the heating, ventilation, air conditioning system. It's typically a system that has its own network, manages the air conditioning, heating of an entire building, and the elevator systems, and so on. Now, these HVAC systems have many times a web portal for the IT people to connect from remote to monitor the system and adjust the temperature accordingly. If you do a quick search in the Shodan.io search engine, you'll find, this is actually a search from a year ago, 36,000 Niagara is an example HVAC system web portal that's been exposed to the internet. And only 269 of those are actually protected with HTTPS. So what the idea is, the attacker would hack the HVAC system, get into that system, because it's not considered a secure system, and he rather easily infect it, and then he'd be able to manipulate the temperature of the building, perhaps at night when there's fewer people there, and broadcast messages to his malware. Now this may sound kind of romantic and kind of like spyware, kind of spy tools and stuff like that, but it's not too far-fetched. As a matter of fact, in 2013, some researchers were able to hack the Google HVAC system in Australia, in the Google office, and they were able to pull out the schematics of the floor plans, change the temperature in the room, and all sorts of different kinds of things like that. So this is what the attack model looks like. As we said, the attacker is somewhere in the internet. He hacks the HVAC system, gains control of it, manipulates the temperature up and down, and sends basically signals 0, 1, 0, 1 to the malwares that are on those computers. So to send a bit, you would raise the temperature in the room. So if it's a 1, then he raises the temperature. If it's a 0, he lowers the temperature. And the receiver looks at one of these thermal sensors in the computer. And if the trend of the temperature room is going up, that means it's a 1. If the trend is going down, that means it's a 0. And if it's more or less staying the same, then he just repeats the same bit as seen in the last interval. Now, to make sense of all this information coming through and make sure that's reliable, it's likely that the attacker will put this bit stream into a typical layer 2 protocol in communication, so basically called framing. So he has, as you can see at the bottom, will send a preamble before a message, 1, 0, indicating there's a message coming in. So if the malware sees that, he'll begin deciphering. An opcode saying what activity the malware should do, whether self-destruct, delete an asset, and so on. A parity bit to help the reliability, and the payload if necessary. So this is just a higher view of the protocol. So you can expect that the malware at night wait during the day, sleep during the day, and then activate at night when there's fewer people around. It'll look for a preamble. If it ever sees a preamble, it'll investigate the frame's integrity. Afterwards, it might collaborate with peers, other malwares in the network, to see if anybody else has received this frame and share this information. And then if everybody agrees that this is a good frame, it will then act upon the opcode and perform the malicious attack. And finally, of course, if a malware doesn't receive any messages within the network, it's likely that's not near any air conditioning system, and then it should self-destruct itself. In other words, delete all traces it was ever there. So in our experimental results in a small office scenario, we got about 40 bits per hour, which is actually quite a lot when all you want to do is send a command saying, start this activity or start that activity. But the question you may think about is, what about internal interference? You know, when a computer is performing different operations, it may heat up, it may cool down, and it may affect the channel that we've built here. So we checked with video playing, web browsing, and word processing. And we found that the thermal sensor on a motherboard is not affected by these typical processes. And it can pick up the temperature fluctuations in the room quite well. To sum up, so the HVACer, what kind of countermeasures can we deploy? So we can disable or at least secure the HVAC web portals. We can monitor the temperature environment for fluctuations that seem suspicious, and we could look for these kind of very specific malware signatures. Let's move over to the next type of method of bridging air gaps through thermal channels, and that's bit whisper. So we know computers can receive thermal signals, but we also know that computers can generate heat. So using these two ideas together, we can make a bidirectional channel. That means if two computers happen to be close to each other, one another, we can have one computer heat up when it wants to send a message to the other, and it can listen also on the thermal sensor if another computer is trying to talk to it. But why is that interesting? Well, a few reasons. Sometimes you have leased computing spaces where you have stacks of computers in a leased space, and one computer may be air-gapped, another computer may not be air-gapped. You may want to send information between one another. Also, in the case of a virtual machine, you may have several virtual computers running in a virtual machine, and you may want them to communicate with one another by heating up the environment and cooling off the environment. So the attack model looks something like this. Two computers next to one another, and they're communicating to one another by raising the temperature or doing nothing, letting the room kind of cool off. So how do they generate heat? There's two easy ways of doing that. You can put a large load on the CPU or a large load on the GPU, and that emits heat from the computer, and that heat is then received by the computer that's next to it, interpreted by the thermal sensor. Okay, so these are the setups that we examined. One computers next to each other, on top of each other, back to back, and so on and so forth. We checked two different kinds of line encodings. The first one on the left is what we kind of did with HVACer. Basically, if it heats up, then it's a 1. If it cools down, then it's a 0. The second one is more of a novel technique where basically we say, let's split up every 16 seconds into 16 intervals. If we ever see impulse of heat, let's say the 7th second, that means we send a binary 7. And then we wait for the next set of 16 seconds, wait for another signal, and that way there's less fluctuations and it's easier to read the signal and have less interference. Okay, some countermeasures for bit whisper, physically distancing air-gapped computers from non-air-gapped computers. We can perhaps have just a strong air conditioning in the room to block out those signals. And we can use malware signatures and environmental sensing. So just a quick demo. Okay, so what you have here is on the left is a computer connected to the internet, supposedly. And on the right, you have a computer which is an air-gapped computer, perhaps a military defense system. And we have, of course, connected to this little military defense system, a little toy missile launcher. And the heat in the room, and the non-air-gapped computer is heating up, setting binary 0s and 1s to move the missile launcher and eventually launch the missiles. In the bottom corner, you can see the thermal signals being sent back and forth between the two neighboring computers. Okay. So that's it for thermal channels. Let's talk about the next type, which is acoustic channels. So the first type of acoustic channel is ultrasonic, done by Michael Hansbach and Michael Goetz. And the idea here is that you can use speakers to emit sound as your transmitter, and you can use microphones as a receiver. And not only that, if you do that with ultrasonic frequencies, the human ear can't pick that up, but the computers can. Thus, you've basically made a covert channel where two computers or even smartphones can communicate with one another if they're in close enough proximity. And I don't know if you've heard about it, but there is a security researcher called Dragos, which claimed he found this kind of malware in his BIOS. And no matter what he did, there's still some sort of communication going on between his computer, sending packets, even known that he had disconnected his network. So the attack model here is you have some sort of mesh network in the air gap side, where one computer holding the asset transmits the information to another computer nearby, and it kind of goes through a random chain in an ad hoc manner until it reaches a computer that's connected to the internet. And then that computer transmits that information directly to the attacker. And same vice versa. If the attacker wants to send a command to the computer inside the air-gapped network, the same process can follow. So some countermeasures, you can put out ultrasonic noise emitters to try and block out that frequency. It won't bother humans, but it'll bother the communication. And you can enforce more stricter zoning policies, making sure that there's no microphones anywhere near restricted zones. The second type of acoustic channel we'll talk about is fan smitter, which is a rather recent work that we did in our labs. And the idea is that computers many times have fans, and we can manipulate the fan speeds, whether it be the case fan or the CPU fan or power supply fan, in order to make different acoustic signals that can be received by a nearby smartwatch or smartphone. But why is that interesting? I mean, we already saw the ultrasonic method, so why would we care about using fans? And the reason is that many times computers don't have a microphone or specifically a speaker to be able to emit these signals. But almost every computer has a fan. So the idea is even if you have like a stack of servers, you can manipulate the fan speeds and thus send information to a nearby computer or smartphone that's listening for those fluctuations. So this is what the attack model looks like. You have a computer infected with malware prior. It affects the fan speeds, and a nearby microphone picks it up and demodulates that information into binary, sending it to the attacker. With this method, we got about 15 bits per minute at a distance about 8 meters, using one of two different kind of modulation techniques. One is ASK, amplitude shift keying, where it's a very basic communication protocol where if you raise the power of the signal, that means it's a 1. You lower the power of the signal, it's a 0. We found there were two interesting properties here, the fan speed and the blade pass frequency. Typically, these will affect which frequency the channel is emitting and what channel you're emitting on. And typically, we also found that most fans have about 7 blades, so the table at the bottom basically show the transmission frequencies, the channel that any malware that would be wanting to listen to this kind of channel would have to be listening on, so that's between about 100 hertz to 550 hertz. The second method is frequency shift keying, where in frequency shift keying, instead of changing the strength of the signal, we change the frequency on which we're transmitting. So in other words, we may speed up the fan faster to a frequency of F1 to transmit a 1, and we may lower the frequency to a frequency of F0 to transmit a 0. And if you can see here the spectrogram at the bottom of a recording of audio, you can see very clearly the fluctuations in the frequency as we're sending 101. So how do you do that in programmatically speaking? So you can affect the BIOS. You can have the malware can try and affect the fan speeds from within the BIOS, or you can just do it through the driver, through the operating system's API, which is a lot easier. For example, in Windows, you can use the WMI, Windows System Management Interface. So countermeasures, like before, zone separation, antivirus monitoring, you can try and regulate fan speeds, noise detection, try and detect these attacks. You can replace the fans with a cooling system, such as water cooling, and you can try and put in insulation to try and mitigate the noise. Okay, I'll just jump ahead here. Okay, so this phone is right next to another computer, another workstation. The workstation is fluctuating the sound via the fan speeds. and it's picking up these hexadecimal values, and it even works while there's music playing in the same room. Okay, the last kind of acoustic channel we'll talk about is disk filtration, and also another new method we came up in our labs. So hard drives also make noise, and the idea here is that if we can change the noise that the hard drive is emitting, then we can, in fact, transmit signals from the computer and be picked up by microphones nearby. So you have the malware on the computer, like usual, affecting how the hard drive is reading information, and that's emitting noise, which is picked up by either a smartwatch or a smartphone nearby. Now, how can you make a hard drive make noise? There are two different acoustic sources. You have the motor, which spins the plates, and you have the actuator, which is the head, which moves from track to track to pick up information. So if you look at the acoustic spectrograms here, we see that read and write and seek each make different kinds of noise across the frequencies. And we found that actually the seek operation made the best signal. And what we did is basically, in order to send binary ones and zeros, we had the head move from one track to another track repeatedly, back and forth, back and forth. If we want to send a zero, we just have it sleep. And if you do that, actually, even with neighboring tracks, then what happens is that the signal comes through very well, and you don't need to jump from one side of the hard disk to another. So some countermeasures, you can replace your hard drives with SSDs. You can get quieter hard drives. You install special enclosures, signal jammers, and zone separation. So here's the computer terminal. It's affecting the hard drive actuator. And that information is being then interpreted by the smartphone nearby. Now, if you think of it, this case may happen quite frequently. Somebody at home in a bring your own device scenario has downloaded a game from the internet, infects his phone, and he brings it to work. He gets to work, puts his phone right next to his computer, and he has no idea that it's picking up information from computers nearby. Okay, so let's talk about optical channels now. So the first optical channel is Tempest. Now, in a paper entitled Information Leakage from Optical Emanations, the authors there showed that the blinking indicator light on hardware actually can divulge quite a bit of information about what's going through that device. So for example, think of a modem. When the modem's receiving information, the light might flicker for every packet or even bit that goes by. And if you have a sensitive enough recording device, you can actually interpret that information going through. So we thought, okay, what if we can actively affect those LEDs to exfiltrate the information we want to send? So we took one example scenario. You have on almost every LCD screen a little LED indicating power. And some of these can actually be affected from the driver. So the malware on the computer will turn on or off the LED accordingly, and a camera nearby can pick up that fluctuations in the light, even perhaps from outside the building via the window. So what we did in order to show that it's plausible, we used an open source library called Open Computer Vision for image tracking. We found where the LED is on the screen. We then extracted the blinking light to interpret binary, and we extracted a binary stream from there. Some countermeasures for Tempest: you can use zoning policies, malware signatures as usual, but the easiest solution is just putting a piece of tape over those LEDs. Okay, so let's talk about the next method, which is ScanGate. So ScanGate was proposed by Adi Shamir and was in collaboration with our labs as well, and presented in Black Hat a few years ago. And the idea is you have office scanners which can light up the room when they scan if the lights are off or at night. And they can also receive information if the room is light enough or dark enough. So we were wondering, how can you exploit that? So one idea we had was you have a malware in the isolated network, and if it wants to send information to the attacker, so it will have the scanner turn on and light up the room a little bit. You have a sensitive camera on a drone outside the building looking at that window, and the light in the room can be picked up and interprets that as binary, sends it over to the attacker, and vice versa. If the attacker wants to send information to the malware, he shines a laser in the room, lights it up ever so slightly, the scanner is scanning and can pick up that light as well. Okay, and the final optical channel is Visisploit. Okay, so we also had an idea, instead of sending typical channels, what if we can hide sensitive information as pictures within the screen? Okay, so you have a typical computer monitor, and you look at that computer monitor as a human, we see whatever image the screen provides us. But if we hide some sort of information, such as a picture or text in that image, it becomes very difficult for a human to see it, but very easy for a video camera to receive that and process that information in post. So we looked at two different approaches. One is typically first of all, eye sees about 72 frames per second. And the computer monitor, typical LCD or LED monitor, will refresh at about 60 hertz. And the idea is if every 60th frame we'll put in a sensitive image, such as blueprints or a QR code, the human won't see it, but the camera will pick it up. And another idea is that the human eye, it's very difficult for it to pick up the difference between two very close shades. So two very light shades or two very dark shades. But using all sorts of post-processing techniques, we can extract that information as well. So we took these two ideas and put them together. And the attack scenarios are where you have some sort of computer terminal, maybe even an ATM machine, and the attacker comes with a camera of some sort and records that screen just for a moment, and then extracts the picture that's hidden in the image. To do this, you actually need to add the malware to have what we refer to as an image concealment module, somewhere between the application and the graphics display driver and interface. So for our experimental results, we tried putting a picture of blueprints on the screen, different text, and QR code. The QR code we use because it's very robust to errors. And we used a whole bunch of different kinds of devices, high-quality cameras, simple cameras, webcams, smartphones. And we had 40 volunteers sit in front of a computer and take a look at the screen and tell us if they see anything strange. And we try to adjust how quickly we'll flicker the image and things like that to find out what's that threshold that the human eye can't see it, yet we get the best throughput. So this is what it kind of looks like. I'm not sure if you can see on the screen so well. There's a QR code hidden in the back of this terminal. After post-processing, it looks all white like this, but you can pick up the QR code quite nicely. Countermeasures for Visisploit. So you can do zoning policies. You can take a look at malware signatures and all the typical methods that we talked about previously. Okay, so that brings us to the final type of channel, which is radio channels. And I like saving the best for last because radio channels are really the most efficient way of getting information out, typically also very quickly, and not only that, but covertly. So let's talk about the first method, which is AirHopper. So in many cases, workplaces that we mentioned before have a policy of bring your own device. Sorry. Okay. And with the bring your own device policy, that basically means that people bring their own device from home to the work. The work doesn't supply their own phones. And we know that smartphones can receive radio signals of all different kinds. So the question was, how can we get computers to emit radio signals? And not just by plugging in a special antenna, how do we get it to emit radio signals without adding any hardware? Purely software-based. Okay? So it looks something like this. You have a computer infected with malware, emitting radio signals to a nearby device. And what's very convenient is that every single smartphone, nearly every smartphone, has an FM chip inside that can interpret and receive FM signals. So all we need to do is be able to affect the FM band, and by affecting the energy on the FM band, we can covertly send information to nearby smartphones. So that's a big question. How do you get computers to transmit radio signals on the FM band? So just a quick aside, how do antennas work? So in order to emit electromagnetic radiation or radio waves, you basically have to oscillate current between two terminals, okay? And radio waves are characterized by two properties: the frequency, how quickly they're oscillating, and their amplitude, how large the oscillations are, okay? So one way to emit EMR from a screen is to send very specific signals to be displayed on the screen. And what happens is the cable connecting to the screen actually emits radio waves based off those signals. Now, I'm not going to go into detail of how to generate those signals. If you're interested in looking at that, you can take a look at our paper. But the general idea is that certain frequencies and shapes affect the signals that are being emitted from these cables, whether it be VGA or DVI and so on. So we took that idea and we tried different modulations that affect the FM band. And in this case, we basically want, since FM is for audio-based signals, so we generate tones. So perhaps a very low tone will be interpreted as 000, a higher tone as 100, and so on. On the computer, you would have some sort of text or information you want to send out to a nearby phone. You convert that to tones based on this encoding, and then you transmit it via FM signals using the idea that we discussed in the previous slide. And that's then received in the opposite direction on the device. The device listens on FM bands accordingly, demodulates information, interprets the binary. So with the experimental results, we got about a distance of between 8 to 20 meters, sending a bit rate of about 10 bytes per second. Some countermeasures for AirHopper: you can have stricter zoning policies. You can provide some sort of insulation, perhaps a Faraday cage if you're really paranoid. You can do jamming if you send out even a light noise, white noise on the FM bands nearby, then you're going to block out the signal. And again, you can try and look for these kinds of signatures in malwares that are trying to do these graphics manipulations. Okay, so here we have a compromised phone and an air-gapped computer. The computer is not connected to any Wi-Fi, no Bluetooth, no Ethernet, completely isolated. Okay, the phone is also not connected to the internet or anything like that. Okay, on the computer, the malware has some sort of keylogger that's listening to keystrokes and transmitting those keystrokes over FM signals through the display cable. So the user types top secret, and it's almost instantaneously received on the phone. Now, as we mentioned, the distance is about between 8 to 20 meters, which means that even if you have a phone in the neighboring room, you can pick up these signals as well. So that's what this is coming to show. Somebody in the nearby room also picked up the message top secret. Okay, so the next paper, GSMEM, was presented at Usenix 2015. And going along with the same lines that bring your own device policy, well, typically in many organizations there's restricted zones, for example, Intel and other organizations. And in these restricted zones, guests or visitors are allowed to enter these zones, but they're not allowed to bring with them smartphones. They're allowed to bring with them feature phones. Feature phones are basically phones that don't have any special capabilities, no Bluetooth, no Wi-Fi. They're like the old kind of Nokia phones. And what we wanted to show is that actually you can transmit information on GSM frequencies. So that's 2G frequencies. And that can be picked up by even a feature phone. And we'll see later also that you can pick it up by any other software-defined radio device, and even pick it up in a better quality. But the question is, how do you get a computer to turn into a cellular base station? Again, without any additional hardware. So what we found is that the CPU to memory bus, in other words, the channels going between the CPU and the memory registers, actually act as a very good antenna. So the idea is that we have the computer send information between the CPU and the memory, and that emits radio waves, and that can be picked up by either a simple phone or a more intelligent phone, or even a very highly catered radio device. So how does it work? So let's talk about emitting a signal. We had two general observations. One, if you make a very large transfer between the CPU and the memory, that emits radiation, but that only works if it's an uninterrupted transmission. Okay, that means that you have to bypass the cache in the CPU. So to do that, you use special instructions that are available in Intel and AMD architectures, and you send a large amount of data to the memory, and that builds up energy on the bus, and then that emits radiation as a result. We also found out that since the typical motherboards have a clock about 800 megahertz, so what happens is that the energy that's being emitted falls out mostly on the 800 megahertz range, which happens to be the GSM range. But it's not just that, we also see that it affects LTE and UMTS technologies as well, 4G and so on. So how does this work? So in order to send a bit, we'll basically do nothing for X amount of time. And then in order to send, for a 0 to send a 1, we'll make a large transmission for a certain amount of time. And we keep repeating that to send all our binary. And of course, like other methods, we can put it into a frame to make sure that we're actually receiving a signal, and also try and do all sorts of different communication techniques, because when you're talking about radio signals, the further away you are and the closer you are, you can move, and that can affect the signal quality. Some properties about the transmitter. The transmitter itself only has a 4 kilobyte memory footprint. It doesn't require any admin or root privileges to operate, and it doesn't use any APIs. And it affects Intel AMD architectures and works on both Windows and Linux. So in order to receive the signal, what we did is, well, first of all, if you want to receive it on a phone, you have to affect the software, or the firmware really, that's written on the baseband chip. Okay, so typically baseband firmwares are closed source and very difficult to manipulate, which is not going to deter advanced persistent threats as we've seen in the past. But for the sake of our testing, what we did is we actually used an open source phone that allows you to actually change the baseband on a Motorola C123 with the open source baseband software Osmocom BB. And in order to show the quality and the, I should say, the possibilities, we took a look at the software-defined radio device USRP B210. Okay, so to receive these GSM transmissions, all you got to do is just listen on the best frequency, i.e. the frequency that fluctuates the least. And we look for the preamble. If we see a preamble, then we say, okay, this is probably a frame. And then we extract the payload. So in our experimental results with the old Motorola phone, we got about a distance of about 170 centimeters. And with the software-defined radio device, we got up to a distance of about 40 meters. And we had two general observations. One is that more channels to the memory, DDR3, DDR4, and so on and so forth, increase the distance, increase the power to the signal. And orientation affects the results. So if the phone is on this side of the computer or that side of the computer, it will affect the quality of the signal. In terms of data rates, with the old Motorola phone, we got about approximately 1 bit per second. But with the software-defined radio device, we got about 1,000 bits per second. So countermeasures for GSM, you can use interference, shielding, again, zoning policies. Don't allow any phones whatsoever into restricted areas, and look for particular signatures. Okay, so here we have air-gapped computer, and in the middle there's a Motorola C123 phone. And on the air-gapped computer there's a keylogger, and the keylogger, sorry, let me skip to the right spot. And the keylogger is listening, picks up the password that's being typed in, and it transmits it through the memory bus to the neighboring phone. Okay, so the final method we're going to talk about today is a very new method called USB, again by Mordechai Guri. Within the leaked documents from the Snowden incident, we found that NSA was using methods of hiding transmitters within USB devices, but that requires adding some additional hardware to the USB devices, although they are concealed. And the idea is, we're thinking that how do we get USB devices to emit radio signals without any additional hardware? How can we have your USB key, when plugged in, emit radio signals? And very briefly, without going into it, because of time, the encoding that goes over the wires for USB write operations is in NRZI. And using that idea, what we do is we send a whole sequence of zeros when we want to send a 1 that causes the signal to fluctuate. And we send a whole sequence of 1s when we want to send a 1 that causes the signal to be solid, in other words, not sending any information. And you can play around with that to send different tones, if you will, over the air to make different FSK modulations. And it's important to note that the malware on the host doesn't require any special permissions to write to the USB. So it can just operate as is without any problems. Oh, sorry, and one more thing. We also noticed that because the USB, or at least USB 2.0 clock speed, has a very particular speed, so the transmission falls out between 240 megahertz and 480 megahertz. So if you're listening on those spectrums, that's where you're going to find the emissions. So from experimental results, we got about a distance of 2 to 3 meters at a data rate of about 80 bytes per second. And all the typical countermeasures can be employed. You can put a Faraday cage if you really want to, distancing policies, and malware detection. So our last demonstration here. Okay, so you have our typical air-gapped computer. On top you see there is a USB hard drive plugged in, and we're going to send write commands to the hard drive affecting the signal that's being emitted from the cable. So right now the device is about to transmit, and in a neighboring room we have a computer with its own little antenna. Okay, and once at the bottom there's a spectrogram there, so you can see how the energy is affected on all frequencies. And the moment it starts sending a 1010, you'll start seeing it in the spectrogram down below. So as you can see, it's very easy to pick up these signals. Okay, so let's make some concluding remarks. So who should be worried about all these different kinds of creative attacks? As a rule of thumb, there are 3 different points you might want to consider. If your air-gapped network is a plausible target for an advanced persistent threat, if your network is very limited with regards to insider activity, in other words, the attacker may be really coerced to try and find these creative ways of getting information out because he may not have perhaps a spy or what have you inside the network to just plug in or exfiltrate the data himself. And if you have strict zoning policies, you may want to consider even stricter ones. In terms of what are the most plausible attacks, we mentioned this already, those pretty much the radio-based attacks, such as DSMM, AirHopper, and USB. Symantec put out a report based off, for example, our paper on AirHopper, pointing out that this is a very dangerous type of attack because it's so covert and rather simple to implement. And in conclusion, how can we summarize? So there's 4 different channels we reviewed today. The assumption, again, I have to reiterate this, that the first step is that the attacker infected the network, the isolated network, with some sort of malware. In some way, the attacker came, he had some insider come and plant a USB device, infected the machines. And after that point, we were wondering how can the attacker send information to that malware and get information out from that malware. The takeaways are air gapping a network is not a guaranteed solution. It does not provide a perfect disconnect, but not everybody is a target. And if you are a target, or you may think you are a target, perhaps extra precautions, zoning policies should be taken into consideration. And that's all. Thank you very much.
Yes, thank you for the very interesting presentation, and very impressive. And my question is, what kind of signature is effective for such attack? You mentioned the signature for multiple channels and multiple times, but I don't think it's realistic to build the signature one by one. I mean the one malware by one signature.
Mm-hmm.
So I want you to share your idea about the signature.
Well, it really depends on the type of channel we're talking about. So if it's a thermal channel, you may want to consider any logic that's reading thermal sensors and trying to interpret it in some sort of way, such as a modulation. So modulation always has some sort of interval where wait 1 second, read, wait 1 second, read, and interpret that as a 1 or 0, 1 and 0 continuously. So that kind of loop, and in regards to some sensor. And again, also with emitting some sort of radiation, there's always going to be some sort of cycle where the transmission is occurring, and it's always going to affect some sort of sensor or some sort of property where you can look for the function calls there.
So, yeah. So you mentioned about the behavior basis signature could be effective for their such kind of attack.
Mm-hmm.
Is that correct?
Yeah, for dynamic analysis. In terms of static, some of these are going to be kind of tricky to detect. You really just going to have to look for the different kind of function calls that are related.
Yeah, I agree.
Yeah.
Okay, thank you. Yeah.